Hello, welcome back. This is Differential Equations by Dr. Oz. In this video, we're going to go through another awesome application of first order differential equations. And the example is about mixture of two salt solutions. So we have a large tank holding 300 gallons of a brine solution already. We already have salt in the brine solution in the tank. What we're doing now is we're pumping in brine solution with some rate, but in the meantime, we're pumping the stirred solution out. It is stated that the incoming rate and the outgoing rates are the same. That means we're going to retain 300 gallons of the brine solution in the tank all the time. The only thing that is changing is the amount of salt in the tank. So initially 50 pounds of salt is dissolved in the 300 gallons tank. What we are interested in is the amount of salt after a long time. And as I said, this is a good application of the first order differential equations. And we're going to set the differential equation up in terms of the rate of change of salt in time is equal to the rate in minus rate out. But you're going to see the details of that within the video. All right, let's get started. All right, first let's split the question statement into three sub-statements. In the first statement, we're being told that we have a large tank holding 300 gallons of a brine solution. It's good. In the second statement, we're being told that salt is entering and leaving the tank in a way that a brine solution is being pumped into the tank at the rate of 3 gallons per minute, and the amount of salt in the inflow is 2 pounds per gallon. And then we mix the solution, and the mixed solution is pumped out at the rate of 3 gallons per minute. And in the final sub-statement of the question, we're told that initially we have 50 pounds of salt dissolved in the 300 gallons, and we're being asked how much salt is in the tank after a long time. All right, let's represent A of t by the amount of the salt in the tank at any time t. So we have the brine coming into the tank with the rate of 3 gallons per minute, and the salt concentration in the inflow is 2 pounds per minute. And we initially have 300 gallons of a brine solution. And after we mix everything up, we pump out the brine with a rate of 3 gallons per minute. And initially we have the amount of salt, 50 pounds. And as you see from this picture, that inflow and outflow is the same, so that means we're going to always have 300 gallons of the mixed solution. All right, let's go ahead and find the incoming and outgoing rates of salt in the tank by looking at incoming rate and outgoing rate. Here we go. So R in, incoming rate, is the product of the rate 2 pounds per gallon, which is the rate of the salt in the brine solution that's pumped in with the rate of 3 gallons per minute. So now we have 6 pounds of salt per minute coming into the tank, and the salt is leaving the tank with the rate of, well, first off, the brine solution is pumped out at the rate of 3 gallons per minute. And remember that pump in and pump out rates are the same, so we always have 300 gallons, and in 300 gallons we have 8 pounds of salt. So in total we have over 100 pounds per minute of salt pumped out of the tank. So for that reason, we can go ahead and write down the differential equation. So the amount of salt, rate of change of salt in time, is the difference between the incoming rate and outgoing rate. And here is the differential equation, and this comes along with the initial condition, which is initially we have 50 pounds of salt in the tank. So this is a linear differential equation. We're going to find an integrating factor, so that is mu equals e to the 1 over 100 dt, and that makes it e to the 1 over 100 t. So why don't we multiply both sides of the differential equation by the integrating factor. So e to the 1 over 100 t dA over dt plus 1 over 100 e to the 1 over 100 t equals 6 times e to the 1 over 100 t. And the left-hand side is the derivative of e to the 1 over 100 t times a, and that's good news. So now we can integrate both sides of the equation to get that you have e to the 100 t a equals 600 e to the 1 over 100 t plus c, an integrating constant. All right, let's multiply both sides of the equation by e to the negative t over 100 to get the description of a of t to be 600 plus c times e to the negative t over 100. And now we know the description of a of t up to the integrating constant c. So why don't we use the initial condition in the next slide to come up with c. So let's just do it real quick. So a of 0 equals 50 means 50 is equal to 600 plus c, and t equals 0 here. So c turns out to be negative 550. So now let's go ahead and write down the full description of the amount of salt in the tank to be 600 minus 550 e to the negative t over 100. Since we have the full description of a of t, we can go back to the very first substatement. All right, since we have the full description of a of t, so we can go back to the third statement of the question, and in fact it was asking how much salt is in the tank after a long time. Well, this is a limit question, so we're going to take the limit as t approaches infinity. As you see that this term is going to approach 0, that's going to make this limit to be 600. Right, this is in pounds, and this is pretty much expected because we have 300 gallons of a brine solution in the tank, and constantly we are pumping in a brine solution with the rate of 2 pounds per minute, 2 pounds of salt per minute. So eventually, after a long time, the amount of salt in the tank is going to make it to 600 pounds. And here is the graphical representation of the amount of salt in time. So as you see that A equals 600 is serving as a horizontal asymptote. So the amount of salt will never ever reach there, but presumably after a long time, as you see that even if you wait for 400 minutes, you're getting closer to 600. If you increase t, you will get closer and closer to 600. Right, we finalized the discussion about this example, and this is the end of the video. Thanks for watching. I'll see you in another video.